So earlier we talked about a classification problem using k nearest classifier. Now let's look into the other type of supervised learning, which was the regression problem. So we'll learn about the linear regression now. The simplest form of regression equation with one dependent or one independent variable is defined by formula y equals to c plus b into x, which is the equation of line, where y is the estimated dependent value score, the c is the constant, and b is the regression coefficient, and x the score on the independent variable. So what it means is that we have some data, imagine it's in our xy plane, our x values are given, and we want a line which best describe uh, whatever the new points will be for particular new x value, will want that y value. And how to get this best line which would describe our linear regression is we want a line which is the error or the difference between our data point and the line which where it goes is, and if we try to add all of these errors or the difference between these two positions, that we want to be minimized. And if we look into the mathematics of the linear regression, it will be quite easy to understand how we can get this line. So as earlier, we have the x and a y, which we talked earlier. We have some x value, and every time according to these x values, we will want to predict the y values. Here, for example, we have, let's say, um, a data where we have four features of house and the final target y, which is the price of that particular house. Suppose there's one feature called size and the number of rooms, floor number, and the age of the house. These are the four features, and then we have the price as a target. Now we want to make a linear regression where according to this x as an input, we want to predict the value of y for some new house. According to the data we have, we want to use the linear regression here. So our problem is nothing but to get that particular best line. Earlier we were talking about only two dimension, but as I said earlier, the x can be is a vector. It can also be a vector, and here it will be this vector of these four features, like in iris dataset. And now we want this y line, which is equals to mx plus c, where x is the feature. So this problem can be made a bit easier if we uh, remove this plus c part and actually add one more feature in the x, and then call the m as a weight, a matrix, a weight matrix. Then our problem will only have y equals to weight into the total x. So if we have a lot of x or lot of features or the lot of data with the all the x as an input, x will be the total number of features. Uh, the x will be finally the number of features we have and number of data points we have, and then some weight and equals to the y value, the real y values. Then we would have solved the whole problem. So the problem finally depends on solving the value for y for w. So this will require a bit of linear algebra, where suppose from the example earlier, y is nothing but 3 cross 1. It had 3 rows and 1 column. The x had 3 rows and 5 column. 4 were the features, and 1 we added one new feature so that we don't want that c part. Then the weight should be 5 cross 3 to satisfy the product of this x and w. Then if we multiply the trans of the x on both left side, we will have a square matrix of cross size 5 cross 5 along with the product of w in the side. Then if we multiply it with the inverse of x trans into x as a whole, then the right hand side will be left with only w, the weight which we wanted, and that will be equals to the inverse of trans of x into the trans of x into y values. We have all of these data, we have the x, we have the x trans, we have the y values, so finally we can get the value of weights like this. So this is how we derive from our mathematical construct. We derive the value of weights which will actually best suit our lines. So now once we have this equation, the weight value, let's try to write some code which we can then calculate this weight and then see how best suited these lines are. So here, for example, if you can see, uh, we have a data which is a random data. We have one added as in the features, and then we have some sort of x and a y values. Then we made these x and y different as x only has now these two columns. One was the real value and one we added one to abolish the value of c. Then to get the weight, we use the same equation which we derived earlier. Weight equals to inverse of x trans dot x trans dot the value of y. Then we got the value of these weights, and these weights are will be the 2 cross 1, which is nothing but the equation of line, which will be y equals to mx plus c. And then we get this beautiful line which best represent these data set which we gave. So this is how we can actually calculate our own weights, and we can do it manually, or we can actually use the sklearn library where you can do it in much shorter way. And let's try to use our linear regression in our in our iris dataset problem. So as I said earlier, all the things below this xtrain, the split between train and test part, will be changed. Above that will remain the same. So let's try to first import the linear regression from sklearn dot linear model. From there, let's import the linear regression, and also let's import our mean square error, which will be useful in seeing how close our model is from the real values. We imported mean square error. So our model will be the linear regression now. Then the model will have to be fit on our X train and the Y train. Model get fits here. Then let's try to predict it using our model.predict, and there we'll use our X train part, sorry, the X test part, and then let's just try to print our predictions. Let's try to run this code. So this is the value which we get. These are the errors which is these are the values which we get for the new X test when on this line when now we give this X test the features, the four features. Now these are the values which the Y that should be in the Y are predicted. Now let's try to evaluate our model performance. We can see as our MSE error, this will be our mean square error between our predictions and the Y true values, which are nothing but Y test. Let's try to print this. So our mean square error is very less. It is 0.045, which means the model is quite fitted on our iris dataset.